organizers for setting up this very nice workshop so far. So the work I'm presenting today here is work in collaboration with Olivier Deluge, who is my PhD student. He's also here in this workshop. So as Slava said, this is a slightly special session in that there are three different persons talking about the same topic. So myself first will go through the introduction to the Lee-Yang. I will have a review to the topic, and then each of us is going to present the results that we got in these different papers that came out the same day on arXiv via coordinated submission. All right. So first I will go through a review about how this theory was discovered. So what was the genesis of this Lee-Yang model? So Lee-Yang many years ago were trying to understand the nature of phase transitions, and their idea was to study Lee-Yang type models. So this is the partition function. Sorry, Ising type models. This is the partition function in a background where you turn on a magnetic field, and they were studying the partition function in the complex plane of this magnetic field. So first of all, you should notice that because these are explicitly a sum over positive terms, and they wanted to study singularities in the complex plane of H, the magnetic coupling. The first obvious thing is that because these are sum of positive terms, the zeros should come in complex conjugate pairs, all right, in the complex plane of H. But there is more to it, and what they prove is this nice thing that the zeros of this partition function in the complex plane of H lie in the imaginary axis. Okay, so the theorem states that when you are above the critical temperature, all the zeros of the partition function should lie on this line. All right, and when you take the thermodynamic limit, these zeros become dense and develop a branch cut. Okay, because these are somewhat surprising theorem, at least it was surprising to me, I would like to go very quickly about what is the idea of the proof behind this statement. All right? Perhaps some of you know it, but I guess that few of you don't know it, so let me quickly review it. So the first observation that Lee-Yang did is that you can map the partition function of the Ising to a lattice gas with this rank canonical partition function, where basically what you do is that you map the spin variables into the density on each side, and now this number density can take values between 0 or 1. All right, this is the first step. And then, so we're going to work with this grand canonical partition function, which is equivalent to the previous one up to a proportionality factor. Okay, and this is the mapping. And also another step to work towards the proof is that we consider a slight generalization. Instead of an homogeneous magnetic field, we turn on a magnetic field on each side. Okay, and later we can take all of them equal at the end of the theorem. Now the Ising symmetry, which flips the spin, and if we also allow us to flip H on each side, this leaves the partition function invariant. All right. On this formulation here, the redefinition is simply this one here, okay? Which what it does is that it takes the inverses of these fugacities, of these i's, okay? So let me quickly tell you what is the gist of the idea, okay? How this can be proved. So we are going to use this identity, which I already showed you, the fact that this is a symmetry of the partition function. And the gist of the idea is to proceed, it's a proof that goes by induction. So the first thing is to prove that there are no zeros on this function in the polydisk, inside the polydisk. All right? First we need to show this. Okay? And then the last step so first I need to prove for you B, and then we are going to use A and V because A sends zeros inside the polydisk into outside the polydisk, and then we're going to conclude that they can only live in the unit circle. Okay, that's the logic of the proof. So now the only thing that I'm missing is to give you the idea of how B is true. Okay, and this is what it proceeds by induction. So if you need for full rigorous, you can go to the actual to this mathematical paper. But basically, the idea is the following. We single out one vertex, say that is vertex 1, let's call, okay? And then it's a simple algebra where you can write the n vertices of this graph as this partition function with the first vertex removed, okay? Plus this term over here. So it's a simple algebra that follows from this formula here. So now what we should now by assumption, because we are trying to build an induction proof, this term do not have zeros inside the polydisk, the one that had a one vertex remove. And now what I want to prove is that this guy over this guy is more than 1, so that we can have a cancellation between both terms. All right. And now to prove that this one is more than 1, basically what one invokes is a generalization of the maximum modulus principle, which applies to multivariate functions that lives in the polydisk. And then basically the ratio of the second term over the first term, okay, attains its maximum in the boundary of the polydisk. And it attains its maximum and is equal to 1. When you evaluate the ratio with all the z's on the unit circle, you can see by eye that this guy over this guy is just 1, and therefore you cannot have other maxima inside the polydisk, and you can never hit 1 anymore inside the polydisk, so you cannot have a cancellation anymore between the two. That's the idea. And so okay, the first few orders of these are easy to check, so that then you are done with this induction idea. Okay. And then we are done, because now we're going to use A and B, which excludes zeros inside and zeros outside. So all these zeros are z equal 1. Z equal 1 is e to the beta h. So it means that all the zeros are purely imaginary h. Okay, that's the idea of Lee-Yang.
Is there some problem with the mic?
Yeah, but no.
I think it's this one.
No, maybe the tissue. Possible. Yeah.
All right. So that was a remarkable observation that they did, a theorem. Now, many
proof works for any dimension.
Yeah, this proof I showed this for any dimension. Yes. Now, many years after, Corman and Griffiths studied this partition function by doing some high temperature expansion, which basically means that you expand in powers of h and compute a number of terms in this partition function in powers of h. And they, what they established, then they studied the density of zeros. And what they observed is that so you can look at the density of zeros by computing some derived thermodynamical quantity, like the number density or the magnetization in the Ising. And what they observed is that this function here, rho of zeta, has some scaling property. Okay, so it has this polar behavior, and they precisely determine in a number of various dimensions the value of this sigma. Right? In D equal 1 can be done analytical, and in higher Ds they provided some estimates. And then there was this other remarkable observation, which came by Fisher. So I guess he did this work soon after his famous work with Wilson. So what he observed is that actually what is called by now the edge of this line of zeros, this edge, which is called the Lee-Yang edge singularity, is actually a proper CFT. So there is a CFT that describes the scaling behavior of this function, and well, he could work out what is the Landau-Ginzburg description, and and it is this one given here. So it contains a phi-cube interaction with purely imaginary couplings, and you can set up some epsilon expansion to estimate the various critical coefficients. I'll say more about this semi-classical description in the next slides. Okay, but for now, let me continue with the genesis.
But where's the density? I mean, so if there are no more any zeros, you're just going to study correlation functions in this Lagrange.
Yeah, so the density
of
of
the zeros.
Sorry?
Where are the zeros?
No, sorry, let me say this more clearly. Maybe it was fast. So the zeros in the thermodynamic limit, they become dense, and then you get branch cuts on the complex plane, and it's the endpoint of this branch cut which has a descaling behavior. So you should approach this scaling behavior is obtained by approaching H critical from the cut. Okay.
No, man, I'm comfortable with correlation functions. The zeros, I was never very particularly excited about the zeros, because what do I do with the zeros? For example, even if I were interested in zeros, how do I know that the density of zeros is related to the correlation functions of the scalar theory that Fisher proposed? How do you relate density of zeros to correlation functions? Is it obvious?
It's not obvious, but I think it was already out in the paper of Fisher.
Thermodynamic limit, the zeros become a branch cut, and I think
Yeah.
discontinuity across a branch cut is the magnetization. This behaves like the magnetization.
All right. So, and then the last point I wanted to mention for there's a lot of noise. The last point I wanted to mention is that
Maybe you could try to stay here further away from the mic.
right.
Yeah.
And now I cannot see a screen.
Well, you can move the laptop closer.
Because there's a mic over there. You're saying.
It's that, yeah, it's probably
Okay.
that.
All right, so, well, then the story continues. We learn about the classification of minimal models by BPZ, and then soon after that, Cardy realized that the simplest non-unitary minimal model in the series actually corresponds to the Lee-Yang theory, to the Lee-Yang CFT that was first proposed by Fisher, and actually, well, I will mention now on the epsilon expansion how it works out. So this is a short recap of how we learn about the existence of this theory. There was a nice review by Cardy recently, where you can find more details of this history. And of course, after this, there are many more results, which maybe later on I will mention few more interesting results on this theory. All right. So now let me mention more about the Ginzburg-Landau description of the model and what do we know, okay? Because this is going to be important for the phi sphere results that we want to check up later. So as I said before, the universality class can be described by the fixed point of this theory. So phi cube has upper critical dimension 6, which means it's marginally there at 6 dimensions and relevant below. So one can set up an epsilon expansion. So the first orders of the beta function for G looks like so. So okay, it has a fixed point. The peculiarity of this fixed point is it is achieved for imaginary couplings of the phi cube interaction. So the potential is oscillating, and this okay, it's a bit peculiar, but we'll see. It still leads to a well-defined theory. As we'll see that later in more detail, because of this imaginary coupling, the Hamiltonian is actually not a Hermitian, okay? But the theory enjoys another symmetry, which it goes under the name often of PT symmetry. So there's a parity that changes the field to minus phi, and some antilinear operation that, which is the time operation, which is I to minus I, all right? So there is no Ising parity, but the PT symmetry acting on the field leaves I phi invariant. Okay. I'll say more about this symmetry from the Hamiltonian picture in a couple of slides. So, because of the presence of this I, there are a number of peculiarities on the CFT that are going to scream at us that it's not unitary. In particular, the scaling dimension of the lowest field, we are going to see that it violates the unitarity bound. All right. And then, all right, the square of OP coefficients are negative. Okay. So these are two weird features. I think I should rush a bit. So very quickly, now we know much more about the epsilon expansion. Actually, it has been computed up to 5 loops. So there are very precise estimates from epsilon expansion of this delta phi, and also at phi cube. So let me tell you a few things that we know about the operator spectrum. Most of it can be worked out starting from the free theory and imposing the redundancies that follows from the equation of motion. So first we're going to have phi and all its descendants. We don't have phi squared because it's redundant with box phi. Then we'll have the T mu at dimension 3. And then the next scalar that comes in is I phi cube. Okay? I'll mention briefly what is soon I'll mention what is the dimension. And then there's the next operator we can write down is a spin 4 operator, for which there are also estimates of the scaling dimension. So all in all, this is the kind of plot that we expect to get from the phi sphere calculations. All right. So in blue is the conformal family of phi. All right. And then we are going to discover from the phi sphere also this operator here and C, the spin 4. And okay, the group of Ruijo et al. Also managed to obtain a new primary that was not known before from previous estimates. And we also see from Joan talk that, well, they managed to refine quite a bit the epsilon estimates for C. And we're also going to have estimates from, well, there were previous estimates on C from conformal bootstrap, a version of conformal bootstrap by Gliozzi. There were also estimates for phi cube. And in the next talk, we're going to see new estimates on all these operators from the phi sphere. Okay, so this is the picture we can keep in mind. All right, so now let's turn on to how actually we're going to do it. So besides this Ginsburg description, this critical point can also be achieved as a quantum critical phenomena. Okay, so what is the idea? Unsurprisingly, the idea is to perturb the Ising in the critical chain, in the spin chain, also by an imaginary coupling. Okay, which is this one over here. This was nicely studied in the 91 by von Gehlen. And so let me review very quickly what it was done in 2D, because we're going to see that many qualitative features are going to generalize to 3D. Okay. So here let me be more explicit now about the PT in this system. So first of all, here again the coupling H violates the Z2 of the Ising, but we are left with this PT symmetry, which can be which is acted by, it can be represented by this operator here, plus the antilinear transformation of I to minus I. So this action leaves H invariant. Now, the action of the PT symmetry, so with the PT symmetry, it's easy using the commutator that to see that the eigenvalues are either real or in complex conjugate pairs. All right? An alternative way to look at it, which I think is the way von Gehlen was looking at it, is that there is a similarity transformation that you can do where you rotate in the xy plane and you send x to y, and this makes the Hamiltonian purely real. Non-symmetric but purely real, and this also makes explicit from the characteristic polynomial that the roots are either 0 or in complex conjugate. So there are these 2 point of views. So what is the criticality here? Okay, or how does it manifest? The idea is the following. When you are at temperatures above the critical temperature, okay, so you are in the disordered phase, the low energy spectrum is non-degenerate. All right. So when you turn this small h, the eigenvalues stay real. Okay. So you really need to crank up h in order for the eigenvalues to become complex. And the phenomena of criticality here occurs because you see that some states collide into complex conjugate pairs. So the picture is this one here. This is how von Gehlen determined the critical point, where you follow the states from h equals 0 to some critical value until they fuse. All right. This was revisited recently by Joan et al. And you will see in his slide that he has some beautiful plots of the 2D story on how they fuse into the complex plane. So, well, also let me introduce a concept that will appear often in the following talks, which is that, of course, the determination of this critical point depends on n, on the volume of the system. All right, and it converges to some Platonic value for h critical when n goes to infinity. But then at finite n's, there are a number of ways to determine what you call h critical. Of course, it's going to depend on your precision of the binning on h and on several other issues. So therefore, we're going to use the nomenclature that for finite n, we're going to be calling it a pseudo-critical, the value of h that we determine, and then the rule of the game will be to understand how these various estimates that you can use for this pseudo-critical h converge into the actual critical h at infinite n. Okay.
Should call it pre-critical.
Or pre-critical. Now, so what is the? Let me show you the plot of von Gehlen. So above, the paramagnetic phase means here a small lambda. Okay, so you're dominated by this guy here. So the Ising sits here, and as you decrease lambda, you are at the high temperature. So once you are here and you turn a small h, as I was arguing before, the spectrum remains real. But now you keep shooting upward until you hit complex eigenvalues. Okay. So the Lee-Yang CFT lives at any point on this line. Okay. And all these points are equivalent because, as I was showing before you with the theorem, okay, this phenomena of the zeros exists for any value of this ferromagnetic cap. It doesn't matter how large it is. So this end of the line exists for any value. So that's why you can take any value of the inverse temperature, shoot upward, and you should hit the Lee-Yang. Okay, that's the idea. This plot here is already like a large n. He has already done some extrapolation. Yes, please.
Sorry, the gap also closes when the eigenvalues bifurcate, or?
Yes. So in fact, this is very clear also in the 3D case because they you can look at different, say, irreducible representations, and the gap is going to close with phi, the lowest scalar, which are on the same symmetry sector.
So all of them bifurcate at the same?
No.
Limit,
so at finite n, it's a mess. So they can bifurcate at different points, of course.
But at n equal infinity?
At n equal infinity, you expect that there is they bifurcate at the same point.
And why does this bifurcation point coincide with with closing of the gap? Is it obvious?
No. The lowest guy is already closing the gap because the lowest guy in the spectrum is phi, which is a scalar, which does collide with identity.
So you're saying the first bifurcation is between the
vacuum and phi. Yes. That's the first bifurcation. And then there are other bifurcations which can happen, which often happen after, when you are at finite n. Okay. In the original paper of von Gelen, all these plots were not shown, and perhaps this is the only plot in the paper, as far as I remember. And then he just comments that, okay, when he goes to large n and he does get all the same critical exponents as the M25.
I understand. If phi collides with the vacuum, we expect that at the critical point, phi energy of phi is not zero. It's negative. So how can it be? There has to be a gap which is equal to what, minus 1/6 over n.
No, not gap collides with the vacuum. I mean, the energy of the energy. So if the gap. I mean the gap of the Hamiltonian, not the delta phi of the. So delta phi is the difference between the vacuum and the first energy state.
Okay, can we go to the previous plot?
Yes.
Can you say which line in this plot represents which state?
Okay, so this is the vacuum, and this is the first excited state.
Okay, and where is the transition point?
Roughly in this dashed region here.
Okay, now I'm saying that at the transition point, between the vacuum and the first state, there has to be some non-zero space, which is going to be over the 1 over n. Should be exactly 0.
Right.
Okay, that's the only point I want to make.
Right, but the right. So exactly, but the point is that it approaches the zero gap with the power predicted by the CFT. So you got a delta phi over r on as it approaches. Yeah. Exactly. All right. So this is the 2D story. And soon we're going to see how this goes to 3D, okay? And many qualitative features follow. Let me mention very quickly, because there's been a lot of literature on 2D Lee-Yang. Let me just point out a couple of things which aren't related to the 3D phi sphere, but I think it's interesting mentioning. So there were a number of recent papers by Zamolodchikov where he studies directly using TCSA perturbations of the Ising. So he sits in the Ising and he turns a sigma and a epsilon, he tunes them and flow to the Lee-Yang. So in principle, this could be something that now could be done in a 3D. So a few days ago, Julia was explaining that he was perturbing, I think, Ising by sigma. So this would be a slightly different thing where you put this imaginary coupling for sigma and also at epsilon, and this should flow to the Lee-Yang in 3D. And then in 2D, it has also been studied directly with Hamiltonian truncation and using the scalar formulation of the theory. Okay, in this recent paper by this group. And I cannot resist also to comment that there's a very interesting thing on the 2D system, which actually there's a single relevant operator, and when you turn it on, it leads to an energy flow to a massive theory, and the S matrix is largely known in this energy flow. It was determined by Cardi and Musardo. It's a pure phase because it's a complex function over its complex conjugate. And the funny thing of this theory is that even though the original theory is non-unitary, even though it's PT symmetric, the S matrix is exactly unitary and well-defined, and it's one of the simplest S matrix. Perhaps later on I'll say more about it.
It's unitary because it's a pure phase.
Yeah.
So the energy flow from Ising to Yang is integrable?
No. All right. No. So what is integral in the Ising is known that if you turn one or the other, either of the two, then it's integral. Where you turn both at the same time, it's not. Okay. And you didn't need to turn both at the same time to break. To have a non-trivial PT Hamiltonian, you need both. All right, so now we take the same problem and we go to the fuzzy sphere. So we put the glasses on. And now, once you know the 2D quantum critical system, it's, at least for the problems we have investigated so far, pretty straightforward how to write down a model. And so this is the model. It's the model of the original Ising in the phi sphere, and we're going to perturb by this operator. All right? Many of the qualitative features I said are going to hold true in 3D, so absence of parity, there's a PT symmetry that we're going to define, and this von Galen curve can also be drawn for this system, and we're going to draw it and see it. So what are we going to see next? Now, so there are two main choices to be made here, which is how you tune the model, and then how you do large N extrapolations. So there were 3 different groups. Each of the 3 different groups come with different ideas on how to tune the model and how to do large N extrapolation, and surprisingly. But all of them are roughly equivalent. So that's what we're going to see next. And before I conclude with the conclusions, with the introduction, sorry, let me mention something I've been asked a number of times. So Yang and Lee put, this genesis of the Lee-Yang CFT started with these 2 papers that were back to back, okay? They were published one after the other, exactly. But the authors decided to sign with Yang Lee the first one and Lee-Yang the second one. So they sort of left it to the community to decide what is the order. Should be said that the first one is the one that contained the idea of studying the partition function in the complex plane, but it's actually the second one that contains the theorem of the zeros. So it's still undecided what to choose. So I chose the alphabetical order, so I've been calling it Lee-Yang, but the other group chose the other order. So in the next talk you will see Yang Lee, but it's the same theory I've been talking about, okay? So now should be Rui Hua who will continue.